The post-Halloween lecture of 2018. All right. So, lecture 3.5, we're going to do a state space model of a translational mechanical system. And it's going to be a little higher order this time. We're going to be doing like probably... Oh! Didn't hit him. So we're gonna be doing a mechanical translational system that's higher order this time. So we did one that's second order. It was electrical last time. So this will be a fun one. So for the translational mechanical system shown, find a state space model with outputs being the spring forces and the mass momenta. Okay. So I didn't give the linear graph here. We have to come up with a linear graph ourselves. So let's, first off, say 0 dot A. We got to do a coordinate arrow. So assign coordinate arrow direction. So we say to the right is going to be positive. We have a velocity source that's applied to this node. It's a massless node in the mechanical system. In a real system, maybe that means that it's a very light mass compared to the other masses in the system. It's negligible in terms of its mass. And we're then going to go through a spring and a damper to mass 1, so a lumped mass, and then through another spring and damper to another mass. So let's do 0 dot B, the linear graph. So it's nice to start with our ground node, right? And let's draw our other nodes too. You've got the two mass nodes, which are pretty easy to identify. They always go to ground, so there's that, M1 and M2. And then VS is applied to another node. So we drew the arrows of M1 and M2 down to ground because they always go to ground. VS, so we have an across variable source in the direction of the coordinate arrow. So we're going to drop away from the node of application, right? That's the rule that we have. So it points down. And then we just have the spring and damper in between each of these nodes. So you've got your K1 and your B1. And I drew the arrows in the direction of the coordinate arrow, right? From the massless node to M1, and then from M1 to M2, K2, B2. Awesome. Okay. 1A, we're just going through our algorithm, right? Our state space algorithm. And we, I think you're just doing it because you want candy.
I ducked my head.
Did you guys notice? I'm doing it underhand. Well, actually, the first one wasn't underhand. Now I'm doing it underhand because it sounds safer. No, I'm surgical with this. Okay, so 1A. Let's do the normal tree. So let's use a different color. Maybe this nice green. And our first types of elements that we take are across variable sources. So we take that velocity source to be part of the normal tree, right? I forgot the nodes. We always take all the nodes, right? Sometimes we just get lazy and don't even do it. And then A-type energy storage elements. So we can take this one, the M1, and we can take M2 as well. And then it goes down to D-type. But if you take either of these two dampers, then you create a loop, right? So that is not allowed. Can't do that. And if you take, and the next one below that is spring, right, or T-type, right? So springs, and springs, if you take either of these two springs, you're going to create a loop as well. So you can't take any of them. So we're done. Our normal tree is finished. So, well, we'll switch back to black here. Okay. 1B. So next it's variables, right? So primary variables and then secondary. Primary variables are cross variables on branches, right? Branches are the elements in the normal tree. So cross variables on them are VS, VM1, and VM2, and through variables on links. So F, the force, FK1, the force in spring 1, FK2, the force in spring 2, FB1, the force in the damper 1, and FB2, the force in damper 2. We just flip all those to get the secondary variables. So we have Fs, the force applied by the source. We have Fm1, the force on mass 1. Fm2, the force on mass 2. V, K1, the velocity drop across spring 1. VK2, the velocity drop across spring 2. VB1, the velocity drop across damper 1. And VB2, the velocity drop across damper 2. Just knocking it out. 1C, state variables, right? I did this without my notes this morning, and I remembered all the steps. It was amazing. I was proud of myself. So I brought my notes this time, but we're going to try not to look at them. Okay. State variables. Don't want to cheat. State variables. So we're going to choose, so we choose state variables always to be the across variables on A-type energy storage elements in the normal tree, right? I know that really just rolls off the tongue, that phrase. We should do it like sing-song. This is a Catholic school. We really should. So state variables are across variables. No, okay. VM1, the cross variable for the A-type energy storage element mass 1 that is in the normal tree. Another A-type energy storage element is in the normal tree. It's mass 2. So we take its across variable as well, VM2. And then we have our forces through variables, or in this case forces, through T-type energy storage elements in the links. Okay, so we've got two of them, the two springs. Springs are T-type energy storage elements. They're in the links, so we have FK1 and FK2. These are the state variables. There are 4 of them, so what is the order of the system? 4. Fourth order system? Crazy, right? That's crazy. Oh man, that didn't go as far as I was hoping. Oh, congratulations. Yeah, the Reese's Pieces don't really fly very well, it turns out. I gotta get better at that. There aren't very many of them. Oh man, they really knuckle. They have knuckle. Did you see that? I was trying to throw it over there. Okay. I'm gonna like hit somebody in the eye, and this video I will not post if that happens. Okay. So we've got our state variables, VM1, VM2, FK1, and FK2. So now we're ready to form our vectors. So the state vector is just a column vector with all the state variables in it. So let's take them in the same order that we wrote them, but that's not necessarily what we have to do. It's arbitrary what order they're in. But once you declare it, you have to stick with it. So we declare it in this step and stick with it. So U is the input vector. We only have one input in this system, right? We only have the velocity source. And then our output vector, which is determined by what we're interested in the system. And it was given in the problem that we're interested to find what the spring forces are and what the mass momenta are. So we've got the spring forces, Fk1, Fk2, and then the momenta, so we'll say Pm1 of mass 1 and Pm2 of mass 2. So those are our vectors, state, input, and output vectors. Okay, 1E. I think we're ready for the elemental equations now, right? Okay. There are 6 passive elements in this linear graph. So we're going to have 6 elemental equations, and we're not going to be able to fit it on the bottom of this page. So we're going to go to the next page, draw a table of 6 elements. And as is the convention that I use, but is not necessary to use, I like to order them in the same order as the state vector first, and then afterwards you just throw in whatever you want. So I'll do M1, M2, K1, K2. So M1, M2, K1, K2. And then the other 2 elements are the dampers, right? So B1 and B2. So the elemental equation for a mass is just Newton's second law, right? So dVm1 dt equals 1 over m1 times fm1. I just realized that the other section is going to watch this video and get the candy thing. Who asked for the Kit Kat? Is that you? Nice. Okay. And then we've got dVm2. So if you're from the first section and you're watching this, I'm not sorry. Oh man. I'm gonna get a bad evaluation just for that. Okay. I'm in a weird mood today. I didn't sleep last night, so I'm just kind of like delirious and having fun. So we've got our springs, which also have elemental equations. Essentially just Hooke's law, but we take the time derivative of that equation. So we get dFk1 dt equals k1 times vk1. And for k2, it's dfk2 dt equals K2 VK2. For the dampers, we just have the force through the damper being proportional to the velocity across the damper with constant of proportionality B1. And it's the same for B2. Awesome. So we've got our elemental equations. So we don't have to scroll quite as much. Let's do 1F here. You have plenty of space, so you can use it how you want. Yeah. No. We're always taking the time derivatives. So the time derivative of x is v. So that's what we've got right here. Time derivative of x is v. Time derivative of f is df dt. So, yeah. So it is, I mean, you're right, the force is a function of the position, but what we're interested in is the time rate of change of the force in this case. So 1F is, we got to do continuity equations, right? Continuity equations. And we're going to do a continuity equation for each passive element in the normal tree. So for each branch, for each passive branch. So we've only got two of those, right? We've only got M1 and M2. So we're only going to have two continuity equations, and they're associated with M1 and M2. So I kind of like this table thing. So we'll go with that. So we need to do a continuity equation for M1 first. So we have to draw a contour, right? It's pretty easy to do this contour, right? We need, remember, we need to cut through or intersect just one passive branch in the normal tree. So that's the M1 in this case, and we were able to do that by just using the simple one around the node, right? So that's what we prefer if we can get away with it. So let's write the continuity equation. So all of the force that leaves this contour in FM1 has to be equal to all the force going into the contour, right? So because FM1 is leaving, so everything going in has to be equal to it. So we're going to say FM1 is equal to FK1 plus FB1 minus, because it's leaving, FK2 minus FB2. So FM1 equals FK1 plus FB1 minus FK2 minus FB2. Sweet. So now we've got to do it for M2. So the contour for M2, we can just do a similar sort of nodal contour, if you will. So FM2, the force going into mass 2, is leaving that contour. And so it's equal to everything going in. So FK2 plus FB2. So FM2 equals FK2 plus FB2. I feel like you guys need some candy love out there. Just doing some candy. Whoa, way back there. Oh, okay. I feel like I keep going here. Oh, you guys down here never get one. So, yeah. Ooh, here's another Kit Kat. Who's really into Kit Kats? Right here, right here. Way downtown, Kit Kat. Oh, don't you play baseball? Okay. Well, to be honest, it was a bad throw. I was never a pitcher, so I was a pitcher in a little league game once, and I wasn't a pitcher like ever, but they were saving like the older kids who were on All Stars. They were saving their arms for All Stars, and so they put me in as pitcher in the it wasn't the ninth inning because we only played like 6 or whatever, but like the last inning of a playoff game, and I lost the game, and I cried after that. That was really sad. That was a good story. Yeah. So pitching was not for me. So compatibility equations. We've got the rest of the elements remaining. All of the links have to have compatibility equations. So we've got K1, K2, B1, and B2. So remember how we find these compatibility equations. We go back to the linear graph and we place each link into the normal tree temporarily, and the loop that's necessarily created, we do the loop equation, like KVL, but we call it a compatibility equation in general. So let's start with K1. So VK1, remember this vector addition way of doing it, VK1 is equal to VS minus VM1. So VK1 is equal to VS minus VM1. And then we've got K2 is the next one I've got here. So if we put K2 in, we've got this loop over here. So we say VK2 has to equal VM1 minus VM2. So VK, that was weird. VK2 is equal to VM1 minus VM2. And notice that these dampers are like the same loops, right? So if you put a damper in instead of the B1, it's just equal to VS minus VM1. So VB1 is equal to VS minus VM1. And VB2 is just equal to VM1 minus VM2, which is to say it's the same as VK2. So we've got all our equations. We've got 12 equations and 12 unknowns. We have a fourth order system, so we got to reduce that down to 4 equations to get the state equation, right? And we are now on part 2A. So we're going to rewrite our elemental equations and substitute in all these continuity and compatibility equations, eliminating all the secondary variables in the process, right? So I didn't mention this when we wrote it. When we wrote the elemental equations, we always write the time derivatives on the left-hand side because we know we're going to want them over there. They're always the primary variables, they're always the state variables. We know that these equations with the time derivatives on them, they're going to be our state equations in the end. But with these other equations, we said that we like to, although it's not required to do it, but we like to solve them for the primary variable in the equation. And FB1 and FB2 are the primary variables for B1 and B2. If you look back at your list of primary variables, you've got FB1 and FB2 up there, so we're good to go. We're already in that form. So we'll use those in their form, and we'll rewrite this table, but this time we're going to substitute in these continuity and compatibility equations. So we've got our M1, our M2, our K1, K2, B1, and B2. So dVm1 dt equals 1 over m1 times, it would be fm1, that's what it was, right? fm1, but now we're going to look for a continuity equation for fm1, and we've got one right here. So it's just equal to fk1 plus fb1 minus fk2 minus fb2. Beautiful. And then m2 is similar. dvm2 dt equals 1 over m2 times, it was fm2, but we've got another continuity equation for that one. fm2 is just fk2 plus fb2 and then k1 was dfk1 dt equals k1. It was vk1, right? But now we're going to get a compatibility equation for it. vk1 is just vs minus vm1. And we can move on to dfk2 dt equals k2. It was vk2, but we've got a compatibility equation for that. Notice that we're going down this list. That's kind of an accident. That doesn't always happen. We don't always get to go straight down continuity through compatibility equations. That is just kind of a nice thing to happen. So don't get too enamored with that. So where were we? We were on K2. So VK2 is equal to VM1 minus VM2. So VM1 minus VM2. And FB1 is equal to B1. It was VB1, but we've got a compatibility equation for that. It's just VS minus VM1. And finally, FB2 is equal to B2 times, and you can see the compatibility equation right here. The bottom one, VB2 is equal to VM1 minus VM2. Whose phone? I'm telling him kind of short because I'm kind of afraid to hit people. Okay. So good. We've got 6 equations now. So we had 12, and now we're down to 6. So that was a big step, right? Let's do 2b, which is to eliminate the remaining non-state and non-input variables. So eliminate. And so which variables are those? VM1, VM2, FK1, FK2, and VS are all good. But what are the 2 variables left that we need to get rid of? Excellent. FB1 and FB2. So, It's pretty easy to do that because these lower equations are just solved for FB1 and FB2. And FB1 and FB2 show up in these equations above, actually just in the first two. These equations are already in terms of state variables and inputs only, right? So it's only these two that need to be modified. But we'll rewrite all of them: M1, M2, K1, and K2. So these are our 4 state equations that are left at the end of all of this substitution. Okay, there we go, straight line. M1, still dVm1 dt on the left-hand side, equals 1 over M1 times, now we've got all of these forces, right? Fk1 is already a state variable, so we can just copy it down, plus Fb1, not a state variable, so we're going to substitute Fb1 in from down there, and we've got plus B1 times Vs minus Vm1 minus Fk2, another state variable, minus Fb2, which we have an equation for down there. So Fb2 is just B2 times Vm1 minus Vm2. Great. So that equation's done. We could simplify, but we're going to write it in standard form anyway, so we might as well just do it when we write it in standard form. Kind of a long equation to keep rewriting. So dVm2 is 1 over M2 times, so it is Fk2 plus Fb2. Fk2 is still a state variable, right? So Fk2 plus Fb2, we can use this equation again and substitute it in there, which gives us B2 times Vm1 minus Vm2. Great. So these are all state variables. These are all state variables and the input variable Vs. And K1 was already in state variables and input variables, so we can just copy that down. dFK1 dt equals K1 times Vs minus Vm1, and similarly dFK2 over, well, dt is equal to K2 times Vm1 minus Vm2. So we have our state equations now. We have the scalar state equations. We want to put them in the vector matrix form, the standard form. So let's do that next. So I'll start it here. 2c. Oh, I got paused again. That's fun. 2c. Let's do the standard state equation. I never look cool when it gets paused. Maybe that's because I never look cool. I'm not sure, but I feel like maybe cooler than these stills depict. Okay, standard state equation, dx dt equals ax plus bu. So let's rewrite that on the next page, but in expanded form. So dx dt is the time derivative of our state vector. So dvm1 dt dvm2 dt, dfk1 dt, and look at this magic, dfk2 dt. So the A matrix is going to be a what by what? 4 by 4, because it's a fourth order system, right? And so the A matrix has to multiply the state vector, which is a 4 vector. So Vm1, Vm2, Fk1, Fk2, a 4 vector. I don't know why I made that so big. And it has to return a 4 vector, so it has to be a 4 by 4. Plus the C matrix, which has to be a 4 by whatever number of inputs, right? So one input, so 4 by 1. I'm just gonna use the green line. Oh, that was a terrible one. That lacked all sense of class. It's terrible. Okay, times VS. So, A matrix, B matrix. I feel like I said C matrix, but it's not the C matrix. This is the B matrix. So A, B. A, B. Okay, so we got to fill this in now. And how we do that is we look back up at our equations. The first one is the one with the most crap in it, so it's going to be the one with the most non-zero elements in the row, right? So let's go ahead and tackle it. Every term has 1 over m1 as part of it. So all of the state and input variables have 1 over m1. Let's start with the first state variable, vm1. It shows up in 2 places. Ooh, I'm back. Vm1 is there and there. So it picks up a negative b1 from this term and a negative b2 from this term. And they're summed together and divided by m1. So we get negative b1 plus b2 divided by m1 times vm1. And vm2 coefficient, looking through here, it only shows up once, vm2. So it's negative b2 times negative vm1, so positive b2 over m1. So b2 over m1. And the fk1 coefficient, looks like it only shows up here, is just 1 over m1. 1 over m1. And the fk2 element is negative 1 over m1. And finally, the input coefficient is b1 over m1. All right. So that was the longest one. The other ones are going to have more zeros in them. So let's see. dvm2 dt is equal to, so we've got vm1 shows up, so we've got b2 over m2. Vm2 shows up, negative b2 over m2. Fk1 does not show up, so it gets a 0. And Fk2 shows up as 1 over m2. And Vs does not show up at all, so the input doesn't show up at all, so we get a 0 for Vs, or for the B matrix in that row. All right, so now we do dfk1 dt, so this third state equation. We only have, for state variables, negative k1 as the vm1 coefficient. And the rest of the state variables don't show up, so they're zeros in this row. And the source does show up, so we get k1 times vs. Okay, and the final one is k1 for vm1 and k2 for vm1 and negative k2 for vm2. So k2 and negative k2. And 0, and 0, and 0. So we have our state equation, our vector state equation in standard form. Beautiful. Fourth order system. Okay, so now we just have the output equation left. So 2C, 2D. So 2D, we have to write the output. The outputs in terms of state and input variables, right? So the outputs were given in the problem as being the force through spring 1, the force through spring 2, the momentum of mass 1, and the momentum of mass 2. So Fk1 is already a state variable, right? So that one's pretty easy. Fk1 just equals Fk1. Fk2 is also a state variable. Pm1 is the momentum of mass 1, which is just equal to the mass of mass 1 multiplied by the velocity of mass 1. And the velocity of mass 1 is a state variable, so we're good. And a similar thing happens for the momentum of mass 2. So we've written all of our outputs in terms of state variables and input variables only. So there are no input variables that show up, which is pretty common. Usually you only need to write it in terms of state variables. In the first example I did, I rigged it so we had an input variable that came in. So, well, I didn't rig it. I mean, it's possible to show up anytime. Yeah? So so FB1 or VB1 or FB1? So FB1, we would have to write that. So say we're like, I'm also interested in FB1. We need to write it in terms of state variables and input variables. It would be nice to go back and look at equations you've already written, because oftentimes it shows up already solved for you, and it does in this case too. So FB1 is just B1 Vs minus Vm1. So we would say B1 Vs minus Vm1. Okay, so let's do our standard form of the output. Standard output equation. We know that it's going to be y equals cx plus du, and our y vector, output vector, let me get classy now, is fk1, fk2, pm1, and pm2. And that's equal to the C matrix. It has to have 4 on this dimension because it has to return a 4 vector, right? And it operates on a 4 vector, the state vector, so it has to be a 4 by 4. I turn my pad and then I can't draw straight lines. Okay, so this is the state vector, so we have Vm1, Vm2, Fk1, Fk2, plus, it's a lot of writing today, my wrist hurts, The D matrix, which has to return a 4 vector, but it operates on a 1 vector, right? So the input vector is only 1 vector, so it has to be a 4 by 1. Okay, so we need to fill it in just from the equations above. So fk1 equals fk1. So fk1 equals 0 vm1, 0 vm2, space it out a little bit, 0 vm2, 1 fk1, 0 fk2, plus 0 vs. So that first row was just writing this equation. Now the fk2 equation, fk2 equals 0 vm1, 0 vm2, 0 fk1, 1 fk2, 0 vs. The momentum, pm1, we have m1 times vm1, 0 plus 0 vm2 plus 0 fk1 plus 0 fk2 plus 0 vs. And finally, we have pm2, which is 0 vm1, m2 vm2, 0 fk1, 0 fk2, and 0 vs. That was our last equation. And we didn't write the suggested v1 in there, but we could have had another row and put that in. So that was just, this was just so extra. Okay. All right, you guys. If anybody wants a piece of candy for the road, you're welcome.